is an area of human endeavor as limitless as outer space, where all progress initially takes shape, where all great achievements begin as human curiosity, the infinite domain of creative thinking. This is the vast realm that is the human mind. Beyond the boundaries of present knowledge are unwritten ideas representing things to come. Only human intelligence can organize the myriad facts and express them in systematic form. Our great and advanced civilization has been built through continuing scientific developments. All the elements, all the metals and materials have existed since before history began. It is only because we have been increasingly able to reach ahead into the unknown that the world of today exists. From early times, devices to assist man in calculating or computing have been employed. But now, computing problems have become tremendous in this age of atomic power and supersonic flight. Repetitive manual labor has been greatly reduced through the use of machinery, but more than that, machines do work that human muscles could never accomplish. Improved automatic devices also are needed to relieve man of repetitive mental work, not only to free the human mind for creative thinking, but to obtain positive and rapid answers to problems, some of which, in the field of sequential calculation, never have been attempted. In addition to such complicated calculations, our modern world depends on fabulously extensive files of data. Valuable time is consumed in locating and referring to this data. In the process of information handling, however simple it may be, memory or information storage is an indispensable element. In adding the products or sums of numbers, the figures must be set down in order. This is the utilization of information storage. To free the human mind from such work, accessibility of information storage must be as automatic as the calculation itself. Years of research developed the fact that electronics could be used both in rapid calculation and for rapid access to stored information. This is now of vital importance. In the work of defending our civilization against aggression, we cannot take time to use the trial and error method in the search for the most practical design for a guided missile. There are also many peacetime problems involving prodigious sequential calculations. For example, a commercial airplane model of the mid-30s required 70,000 engineering man-hours. The modern airliner requires approximately 12 million engineering man-hours. This is a significant example of today's tremendous computing and processing problems. We can only estimate what tomorrow's designs will demand in time and effort. To meet these ever-increasing problems, IBM now presents the first of a new line of equipment known as electronic data processing machines. These several machines work together as a unit to provide one of the fastest and most versatile means known for the processing of data. New principles have been applied to provide vast capacity for the storage of data and instructions. In magnetic tapes, in magnetic drums, in electrostatic storage. This data can be made available in a few millionths of a second for use in the arithmetic unit. Work which would take even recent electronic sequential calculators 50 hours to do this equipment can accomplish in less than 7 minutes. Such an achievement did not happen overnight, but was developed over a long period of years by scores of scientists and technicians, and was based on decades of experience in manufacturing machines for use in business offices. This association with business and science revealed the vital need for electromechanical devices which could perform advanced computing operations. It led to the first of 7 significant steps in the growth of today's giant calculators, when in 1929, construction and testing of the first calculating machine to compute and print mathematical tables was completed. This statistical calculator was presented to Columbia University in December of that year. Then, in 1934, interest stimulated by the work performed on this calculator led to the founding of the Thomas J. Watson Astronomical Computing Bureau at Columbia. Here was a new departure in scientific calculation. Tiresome additions, subtractions, multiplications, the looking up of numbers and tables, the reading and writing of figures, all were done by the machines. The need for devices which could go beyond this and actually assist in solving mathematical equations was first filled by the automatic sequence controlled calculator. This, the first giant calculator, was composed of electromechanical devices and was dedicated at Harvard University in 1944. It was immediately applied to the solving of sequential calculations in naval ordnance problems. In 1946, after years of research, electronics was applied to the first production line electronic multiplier when the type 603 was announced. This was expanded 2 years later into the type 604 electronic calculator, which is capable of performing 60 operations in a problem at a constant speed of 6,000 problems per hour. Such speed is possible because electronic devices have the property of producing rapidly recurring pulses and can be used to count at extremely high rates, up to millions of times per second. The 604 is so widely used in industry today that it is being built on a production line basis. Each machine employs 1,300 electronic tubes. This experience in electronic research and application in 1947 led to the building of the Selective Sequence Electronic Calculator, which was installed at IBM World Headquarters in New York. The SSEC solved some of the largest mathematical computations ever completed up to that time. For example, scientists encountered a problem dealing with splitting the uranium atom, requiring 9 million sequential calculations. A mathematician working with a desk calculator would have had to labor over it for 100 years. The SSEC produced the answer in 100 hours. In 1949, the card-programmed electronic calculator was announced. Designed for scientific and engineering sequential calculations, this computer was organized from regular production machines. Instructions originate from punched cards fed into the card reader, from which figures are placed in the storage unit for later use or sent on to the electronic unit, which can calculate more than 80 multiplications a second. The answers may either be printed or punched in cards. Meanwhile, in the IBM laboratories, research was going on more intensively than ever. Machines were needed with greater speed, greater storage capacity, and great flexibility. Extensive research was made into all available electronic tube designs to develop them to meet the precise requirements of computers. One such accomplishment is the cathode ray tube, developed for use as an electrostatic storage unit. Each cathode ray tube can store the equivalent of 140 decimal digits. Random access to these is almost instantaneous. In a few millionths of a second, any number stored on a tube may be selected for use. Information is stored on the screen of the tube through the presence and absence of charged spots. A scanning electronic beam reads these charges and converts them into electronic pulses. The pulses are interpreted as numbers or instructions. Another component developed as a storage medium is the magnetic drum. These drums are rotating cylinders surfaced with a material which can be easily magnetized. Thousands of digits are stored on the surface of the drum through the presence and absence of magnetized areas. As the drums rotate and are read by many reading units, all the information on their surfaces is available thousands of times a minute. Still another development is the magnetic tape. The tapes are plastic oxide-coated ribbons with information recorded on them by means of magnetized spots. The information in several office filing cabinets can be stored on one reel of tape. It is possible to record data onto the tapes or to read information from them at the rate of thousands of decimal digits a second. Such components are being investigated and developed constantly. Thus, when accelerated national defense created a need for a better calculator, the components were ready. These new principles now have been incorporated in the electronic data processing machines, and they are ready to assist in solving the complex problems which defense measures in an era of supersonic speed and atomic power have created. For example, a rocket cannot be aimed like an artillery shell, whose weight does not change and which coasts to its mark. The rocket becomes lighter as its fuel burns. Its motor exerts a changing thrust as the fuel is exhausted. And there are many other factors to be considered, and each may change in the fraction of a second. The trial and error method cannot be used. We must know before we build the rocket exactly how it will behave. To calculate this, we take all factors into account and plot the missile's path in intervals of 1/10 of a second for the required length of time. For a typical calculation performed on the card program calculator, 75 seconds are required for each point on the path, or a total of approximately 2 hours for one set of conditions. Since we must study, in this case, the paths for at least 25 different designs, approximately 50 hours were required on the card-programmed calculator. Now, electronic data processing machines can perform all these sequential calculations and print the results for the 25 sets of conditions in less than 7 minutes. Now, more time will be available for pre-testing each model, as well as for creative thinking. To illustrate the great potentialities of this equipment, let us trace this problem briefly as it proceeds through the machines. On a few feet of magnetic tape, the weights, thrusts, and all other basic information for the 25 different rocket designs are recorded. Also on tape are recorded instructions to tell the equipment how to do the problem. When the equipment is started, the instructions and data are read from the tape at a rate equivalent to 12,500 decimal digits per second. The instructions and data then pass to the electrostatic storage unit, where they appear on the cathode ray tube screens. Part of the information instructs the machine to begin the program and carry out the specified calculations. Instructions and data go back and forth between the electrostatic storage and the arithmetic unit, and computing is accomplished. Intermediate results are recorded on the magnetic drum to be available when required, all under control of the instructions originally stored on the magnetic tape. The results are recorded on the tape for permanent storage or recorded by the printer. In this problem, the values are printed for each second of the rocket's path, for the velocity, position, acceleration, yaw, pitch, and roll of the rocket. The final values tell where the rocket will land. All of the data, not only on one rocket design, but on 25 variations, are produced in less than 7 minutes. Thus, it is now practical to investigate hundreds of detailed designs because of the tremendous capacities and speeds of this new calculator. The reading speeds are significant. Writing is not only fast, but versatile. Processing speeds permit computations in microseconds. Storage is vast and flexible. This is a triumph of advanced storage and calculating techniques, components developed against a large background of research. A triumph, yes, but no matter how great a thing is, there is always room for improvement. Today, the components and parts, the machines of tomorrow, are taking shape in the research laboratories. In order to ensure that no approach has been ignored, researchers are studying the characteristics of many different elements. One component being investigated is the transistor, a small piece of germanium and wire. There is also research in progress pertaining to magnetic cores and ferroelectric materials. The defense effort has taken priority, but advanced studies are underway to adapt new electronic components for service in business. For electronics is the fastest and most versatile means known for handling accounting and statistical data. The people of IBM long ago took the lead in this field and are maintaining it with advanced production methods applied here to the new electronic data processing machines being assembled. Yes, new progress is being made because the electron, the smallest particle in nature, has been harnessed to count. and brought to the aid of scientists and businessmen who are expanding the frontiers of knowledge. For after all, the real barrier is time. The shape of things to come may now be resolved in decades instead of centuries. The years may be compressed, the future's stream accelerated, because the human mind has been relieved of much repetitive work to devote itself to creative thinking, to go on, piercing the unknown.